Welcome to the Ultimate Physics channel. The topic of this video is solving problems on Lorentz transformation in special relativity. There is already a video on Lorentz transformation, which is a lecture video. So those of you who haven't watched that video, I recommend that you watch it first before trying to solve these problems in this particular video. Anyway, I will quickly do a recap of the equations of Lorentz transformation so that there is some familiarity while solving the problems. So basically, the Lorentz transformation equations are used to transform the spatial and temporal coordinates of a point or an event occurring in one frame of reference to another frame of reference. So these are a means of transforming the coordinates of a particular point or an event. From the coordinate transformation equations, one can also derive the velocity transformation equations, right? So for a set of coordinates x, y, z and t, that is a time coordinate, belonging to a frame of reference S, the corresponding set of coordinates in another frame of reference S prime, which is moving with a velocity, relative velocity with respect to S in the positive x direction. If the relative velocity is a small u, then the Lorentz transformation helps us to transform the x, y, z, t to x prime, y prime, z prime, t prime, that is from frame S to frame S prime. Now the actual equations are x prime is equal to x minus ut over square root of 1 minus u squared over c squared. We know that 1 over square root of 1 minus u squared over c squared is equal to gamma. That's a Lorentz factor in special relativity. So you have gamma times x minus ut as a shortened form of this equation. So this gives you the x prime coordinate from x coordinate and t coordinate in S frame of reference, let's say. Right, u is of course the relative velocity between the two frames of reference, and c is the speed of light, which is equal to 3 times 10 power 8 meters per second. Right, y prime is equal to y and z prime is equal to z. That is because our two coordinates do not undergo any transformation. The relative motion between s and s prime is along the direction x, common x direction between the two frames, and therefore you can see that the relative motion is along the x direction. That is in right like this, right? This is the x direction. Let us say this is the origin of S frame of reference, and the S prime frame of reference has an origin O prime, and this is x prime. So the direction of motion is in this direction with velocity u, which is a relative velocity between the two frames. So it is parallel to the common x direction, so to say, and that's why the y coordinate and the z coordinate, they do not change. They do not undergo any transformation in this case. The time coordinate transformation is t prime is equal to t minus ux over c squared in the numerator over square root of 1 minus u squared over c squared, which can again be shortened as gamma times t minus ux over c squared. Now these are the set of transformation equations for coordinate transformations from S to S prime frame of reference. One can also do the inverse transformation, that is from S prime to S back, and that is by changing the signs and the coordinates. S prime coordinates will replace the S coordinates on the right hand side of these equations, so the equations will look similar otherwise. So you have x is equal to x prime plus ut prime over square root of 1 minus u squared over c squared, which is equal to gamma times x prime plus u t prime. So you can see that right hand side now we have the coordinates corresponding to the s prime frame of reference, whereas left hand side we have the coordinate required, that is s frame of reference. Now y is equal to y prime and c is equal to c prime, and time is t is equal to t prime plus u x prime over c squared over square root of 1 minus u squared over c squared, which is equal to gamma times t plus ux prime over c squared. So these are the coordinate transformation equations that we would be using in our problems. Now we also have a set of velocity transformation equations between the two frames of reference, that is from s prime to s transformation. That is, if you have a set of coordinates, velocity values rather, for the s frame of reference, you can get the velocities for a particular object moving in s frame to s prime frame, right? So the coordinates for an object in s prime, if it is known, so vx prime in this case is equal to vx minus u over 1 minus vxu over c squared. Vy prime is equal to Vy times square root of 1 minus u squared over c squared over 1 minus Vxu over c squared, and Vz prime is equal to Vz times square root of 1 minus u squared over c squared over 1 minus Vxu over c squared. These are the three equations that we will be using in our problems for velocity transformations. Here, the relative motion, of course, is in the direction of x, common x direction between the two coordinate systems. Yes, we have discussed these equations in our lecture video, so I advise that those of you who haven't watched the lecture video, please go and do so that you'll have a clearer understanding of the Lorentz transformation before solving the problems. Here, particular thing to note in the velocity equations is that the x coordinate belongs the x coordinate depends in the s prime frame on the velocity along the x direction, as well as this vx repeats here. Please remember, because some students I see that they tend to forget this and write vy here, vz that, but that's not the case. Here it is again vx only, here also it is again vx only. So because the motion is along the x direction, the velocity component in that direction only matters here, whereas the numerator you have vy and vc correspondingly, right? So with that in mind, let us move on to the problems. First problem is the coordinates of an event occurring in inertial frame S, or x is equal to 75 meters, y is equal to 20, z is equal to 40 meters, and the time is 2 times 10 power minus 5 seconds, right? So we have got x, y, z and t in S frame of reference. Now another inertial frame S prime moves with respect to S with the relative velocity u is equal to 0.85 times c. That is the speed of light. The origins of S and S prime coincided at t is equal to t prime is equal to 0. Now first part of this question is find the coordinates of the same event in S prime, and then the second part is verify by doing inverse Lorentz transformation that the original coordinates of S can be obtained. So the first part is pretty simple. Directly apply the Lorentz transformation equations to get coordinates in S prime. We are going to use those equations and try to get that. The second part is just a recalculation by substituting the values we have obtained here to get back these values. We have to try to get these values again, right? So that is what we are trying to go into. We are trying to go to. Okay, so let's start with it. So we can write that we need x prime, which is equal to gamma times x minus ut. Of course, our y prime and z prime are going to be the same. And then of course we will calculate a t prime using the formula t minus ux over c squared by, of course, square root of 1 minus u squared over c squared, or gamma times this thing you can write in a shortened format. Now, we have to first calculate gamma in these problems. That's the first step. So gamma is 1 over square root of 1 minus u squared over c squared, which is equal to 1 over square root of 1 minus, here it is given as 0.85 c, right? So I put 0.85 squared here, c squared, denominator there is going to be a c squared, and that they will cancel. So you effectively have, if you do the calculations, gamma as 1.898. In such problems, in relativity, special relativity, the number of significant digits that you take in your calculations matter a lot. Otherwise the answers would be way too off the mark if you make a small mistake in these values of beyond the decimal places. So it is better to take accurately as many digits as possible in the initial cases, so that we don't offset the values by too much. Now, if I calculate x prime using these values, I substitute gamma in its position, and then I multiply that with x, which is 75 given here in the problem, minus u is 0.85 c, so 0.85 into 3 into 10 power 8. I am taking the c to be 3 into 10 power 8, multiplied by the time that is given here, that is 2 into 10 power minus 5 seconds. So it is 2 into 10 power minus 5 seconds, right? So if I do the calculations, I'm going to end up getting x prime being equal to negative coordinate, so minus 9539.04 meters. So this is my x prime coordinate. Of course, my y prime is going to be therefore equal to y, which is equal to 20 meters given here, and my z prime is going to be equal to 40, which is same as z coordinate, right? So now that we have done this part, we have to now try to get the time coordinate, right? So it is t prime is equal to gamma times t, so 1.898 in our equation, and the time is given as 2 into 10 power minus 5 minus ux, so it is 0.85 c is your u, and our x is 75 over c squared, that is another 3 into 10 power 8 whole squared. So I'm cancelling this from here, and therefore whatever I have, that remains, and I end up getting t prime as, if I do the calculations, please do check out these things. So it is 3.756 into 10 power minus 5 seconds. This is the time coordinate. So now we have got the set of coordinates in S prime frame of references by doing the Lorentz transformation. So we got x prime, y prime, z prime, and t prime. This is the first step, so we have done that now. Now the second part of the problem, which is the B part, is to reinsert these values and get back these coordinates, the reverse, right? This is the second part now. So we have x prime is equal to gamma times x is equal to gamma times x prime plus ut prime. This is the inverse, right? So we are going to try to do that now. So our x is equal to gamma times, so 1.898 times our x prime is minus 9539. So we got that, right? I'm trying to use those values now to get back these things, plug in those numbers and try to get this. So that here it is 0.85 into c u, right, u, and um, so your u is here, t is we have calculated, right? So that value has to be plugged in, 3756 into 10 power minus 5, right? So this is u t prime. Of course, our gamma is outside, so we don't have it denominated here. This directly we can do it. So we will get here our x to be back equal to roughly 75.06 meters. So I write it as directly 75 meters. Important here is that this particular calculation, if these numbers are not taken accurately, there is small error in these numbers, let us say, or you round off at wrong times, then your values here will be too offset, way too different from the actual values. That is not an error in your calculations per se or in your methodology, but that is because of the accuracy of the values. If that is slightly different, then your values will be too offset, as I said earlier. Now y is going to be 18 meters. There is no change in y or z, so you don't have to kind of do any calculations for that. And then time, again we can try to get that. T is equal to gamma times t prime plus ux over prime over c squared. So this one, if you try to do, you can get 1.898 times our time is here, so we put that 3.756 into 10 power minus 5 plus 0.85c, again the same thing. And then our coordinates is minus here, minus 9539.06, same whatever we obtained or we used here, 04 other, over 9 into 10 power 16, that is 3 squared. Or you can put 3 to 10 power 8 over whole square, so this 1 will cancel, you will end up with having 3 into 10 power 8. And then if you do this calculation again, you will exactly get it is equal to 2 into 10 power minus 5. I encourage the viewers to verify this. 10 power minus 5 seconds, reasonable accuracy. So that sums up the problem. It completes the first problem. Let's move on to the next one. The second question is, two spaceships are approaching each other. What is their speed relative to each other if their speeds relative to the Earth is 0.9 c? So we have Earth, we have two spaceships approaching us, right? So let me try to draw some spaceship kind of thing here, and then let me kind of repeat that here as well, because they are identical in all aspects. Let's say they're approaching each other, and the approaching velocities with respect to Earth they're asking, but the relative velocity between those two spaceships is 0.9 times the speed of light, c. Now this we have to use the velocity transformation equations, velocity equations we have to use, right? So to solve this, we have to use the velocity equations. So we know that Vx prime, for example, is equal to Vx minus u, if the relative velocity is u, over 1 minus Vx times u over c squared, right? This is the velocity transformation equations in the x direction. And then of course the Vy prime and Vz prime are there, but we don't have to calculate those because we can consider here only motion along the one direction. That is enough for us. We calculate because it is only one velocity coordinate is provided here. So we could fix the, let's say, the frame of reference S on the Earth, and then we could fix the S prime frame of reference on one of the spaceships. So let us call this spaceship as A, this spaceship as B, and therefore I fix the S frame of reference on Earth, and I fix the A spaceship, the S prime frame of reference on spaceship A. Okay, so this is a spaceship A, this one. So this takes S prime. Now we can calculate, therefore, using these equations, the velocity of this object B, that is the spaceship B. So I can write the velocity of spaceship B with respect to spaceship A is what? So in this case, that is, let us say Vx prime. We need Vx prime, so we say that is Vx prime is equal to, we have to use this equation. What we have already, Vx, which is the velocity with respect, velocity of the spaceship with respect to Earth, that is given as 0.9 c. So since these two are coming in opposite direction, we have to take this as negative 0.9 c. Minus 0.9 c we have to take, and the relative velocity is u between the two frames, that is S and S prime, that is again 0.9. So if one is negative, the other one is therefore positive, so it is 0.9 c. So we can substitute those values here. So our formula is again Vx minus u. So Vx minus u over 1 minus Vxu over c squared. So it is minus 0.9 c minus u is again 0.9 c. So I put 0.9 c here, and then here I get 1 minus minus is there, so minus 0.9 c, so minus becomes plus here, 0.9 times 0.9 over c squared over c squared here. So these two c's, so in the numerator becomes 0.9 times 0.9, and that is 0.81 c squared over c squared. So that will cancel, so we have minus 1.8 c over 1.81. That turns out to be 0.9945 c. So that is the speed of a spaceship V with respect to Earth. Its speed with respect to the other spaceship was 0.9 c. The speed of spaceship A with respect to Earth was also 0.9 c, whereas the speed of B with respect to Earth is calculated to be rather 0.9945 c. So that solves the problem number 2. Yeah, let's move to the problem 3. A particle moves with speed 0.9 c along the x double prime axis of frame S prime, which moves with speed 0.9 c in the positive x prime direction relative to frame S prime. So here there are two different frames that are given, and a particle's velocity in one frame of reference, that is S double prime, is given, and then the relative velocity between the two frames S prime and S double prime are given in the first line of the problem statement. Next line is frame S prime moves with speed 0.9 c in the positive x direction relative to frame S. So here again relative velocity between two other frames are also given, that is between S prime and S. Now there are two steps in this problem. The first step A is find the speed of the particle relative to frame S prime. Next B, find the speed of the particle relative to frame S. So if we can make a small diagram, we can get the situation clearer in our mind what is given here. Okay, so here we have first, let's say, S frame of reference. This is yes. Then we have another one parallel to, let's say that is S prime. And then we have a third one as well here. So here it is 3 frames of reference that are compared. So we have S double prime here. Okay. So what is given here? First, some particles velocity is given. That is 0.9 c with respect to S double prime frame. So I say there is a particle here, and that is moving with a velocity. Let me take that as Vx type prime double prime, because it is velocity of a particle, right, in the S double prime frame. So we can say by our convention Vx double prime as 0.9 c. Now this frame S double prime moves with respect to another one S prime with a velocity 0.9 c. So that the velocity relative motion between these two is given by velocity 0.9 c, which again in turn moves with respect to another frame S with the velocity 0.9 c. So it seems a tricky one initially, but we have to just apply the Lorentz velocity transformation equations twice to get the answer for this question, right? So the first step is find the speed of the particle relative to S prime. So let me do the A part first. The velocity of the particle Vx prime with respect to S prime is Vx prime, right? So Vx prime is Vx double prime plus u. See, remember here it is from S prime to S double prime, so we have to use the inverse velocity transformation equation. So it is 1 plus Vx double prime u over c square. This is the equation we have to use here. So it is Vx plus u. Vx double prime is 0.9 c, and plus u is again 0.9 c here, so 0.9 c over 1 plus 0.9 c squared, 0.9 into 0.81 c squared, so 0.81 c squared over c squared. So again it is 0.9945, something similar to the value we obtained in the previous problem. So we can directly write that. The first part is done. The next part is, again, we need Vx now, right? Because the velocity with respect to S frame, so it is Vx, and that is from S prime we need. So we have Vx prime. That is also another inverse transformation only we are doing here. Vx prime plus u over 1 plus Vx prime u over c squared. Therefore it is again here Vx prime we have calculated as 0.9945, so 0.9945 plus u is again 0.9 c in this case also, so it is 0.9 c over 1 plus 0.9945, 0.99 c 45 plus 0.9 c squared, denominator c squared will cancel. Therefore we can say that the answer, if you calculate, is going to be 0.9997 c. Okay, this is the velocity of the particle with respect to the frame of reference S. So that completes our third problem. Okay, the fourth problem is the origins of two frames S and S prime coincide at t is equal to t prime is equal to 0 seconds. That is, initially at t is equal to 0, the two frames are, their origins are coinciding. Their x-axis x and x prime are parallel, and their relative motion is along the common x direction, x prime direction, that is ox direction, because origin is O, with a speed 0.5 c. An event occurs on x-axis at 10 light seconds. So some event occurs at 10 light seconds at time t is equal to 4 seconds in the S frame. What are the coordinates x prime, y prime, z prime, t prime in S prime frame of the same event? So that is a question. So we have two coordinates here, S prime. The origin is O, x here it's O prime, X prime is the direction here. This direction is a common direction in which the relative motion between the two frames occurs, and initially they coincide at t is equal to 0, the origins O and O prime, and some event occurs at 10 light seconds. So the coordinate x is given here, in this case, as 10 light seconds. 1 light second is, we know that distance light travels in 1 second, and that is 3 times 10 power 8 meters, because speed of light is 3 into 10 power 8 meters per second. So in 1 second, light second, so 10 we have here, so we have to write here 10 into 3 into 10 power 8 meters. That is x coordinate. Y coordinate and z coordinate are not relevant to calculations, so we can say that whatever it is not a big deal. The relative motion here is u. Let us take that as 0.5 c is given here, so it is u 0.5 times c, and time coordinate here is 4 seconds. So we'll calculate x prime using our transformation equation, gamma times x minus ut. Right, x prime is equal to gamma times, what is gamma here? Because it is 0.5 c, I calculate gamma here. It is 1 over square root of 1 minus 0.5 squared. That is going to be equal to 1.155. Okay, so 1.155 times x is 3, let's say 30, let us say 30, because 3 into 10 I do, 30 into 10 power 8 I retain, minus ut. U is 0.5 c, so 0.5 into 3 into 10 power 8 into time is 4. Okay, so that is going to be 10 minus 2, because here we have 3 into 10 power 8 as common. If I take it out, I can write x prime as I get, if I do the calculations, 2.77 into 10 power 9 meters. This is what I'm getting as x prime coordinate in this case. I can also calculate the t prime coordinate, because my y prime is same as y, whatever it is, z prime is equal to c, so no problem. T prime is equal to t minus ux over c squared, multiply the whole thing by gamma, of course. So it is again, we do the calculations in this case. Yeah, t prime is equal to gamma times t, which is given as 4 seconds, minus ux, which is 0.5 into 3 into 10 power 8 for u, multiplied by x is given in this case as 30 into 10 power 8, that's 10 light seconds, right, over 3 into 10 power 8 whole squared, c squared, right? So I say that this is, now this whole thing will cancel, because here we have 1 and then here also we have 1, 10 remains, isn't it? It is basically 5. So for 1.155 times 4 minus 0.5 times 10 is 5. So I have minus 1 here, it is. So the coordinate here is a negative coordinate that we are getting, that is minus 1.155 seconds. That means, what is the meaning of this negative sign here in this time case, t prime? The event, this means what? This means the same event occurs in S prime frame 1.155 seconds before, because of the negative sign, we say that it is before it occurs in S frame, right? So that is the conclusion we can draw from the result we have obtained here. So let's move on to the next problem, that is the fifth one. Two inertial frames S and S prime are in the standard configuration, that is again the origins are coinciding at t is equal to t prime, and the x-axis, the common x-axis is parallel, and relative velocity u is along the OX direction. Two events are occurring with an interval 4 seconds at the same place in S frame. If the time interval between the two events is 5 seconds in the S prime frame, what is their spatial separation in the X prime frame or direction? And what is the value of the relative velocity u between the two frames of reference? This is the question here, right? So here, what is given here is two events are occurring in two different frames. The interval between the two events is 4s in S frame of reference, but it is occurring at the same place. So we can say that since it is occurring at the same place, let us call the two events coordinates in S frame as x1, y1, z1, t1, event 1. Okay, in S frame. And then event 2, x2, y2, z2, t2. Now the separation is the differences, right? So I say in the S frame of reference, del x is the separation in x direction, and that is x2 minus x1. Of course, the del y will be there, del z will be there, which are y2 minus y1, z2 minus z1, but we don't have to bother about those calculations because the direction here is along only the y direction, relative motion. And then there is some time difference as well, right? So that is del t, time coordinate. That difference is t2 minus t1, and that is given here as 4 seconds. And it is occurring at the same place, so our del x is equal to 0. So del x is 0 and del t is 4 seconds. This is for frame S. Now the question is, in frame S prime, what is their spatial separation? That is, del x prime is what? Right? And the two events are separated by 5 seconds in this frame, so del t prime is given as 5 seconds. And then relative velocity between the two frames are going to be what? Is u, let's say. Okay, doing our calculations. What would be the relative velocity? There is a question here. You can try to solve this one. So based on the Lorentz transformation equation for x prime, we know that is gamma times x minus ut. So if we do for two such events, then we'll have del x prime is equal to, following the same equations, we can get gamma times del x minus u times del t. Since del x is 0, we say that del x prime is equal to minus, this minus sign is there, so minus gamma times u times del t. This is one equation we can straight away write. On the other hand, we know that del t prime can also be written in the same fashion as gamma times del t minus u del x over c square. So we can derive these difference equations from our original Lorentz transformation equations for two sets of coordinates, because there are two events here. Here, since del x is 0, that is given here in the question, because at same position the events are occurring in the first frame. So this term vanishes. We have only del t prime is equal to gamma times del t, and del t is 4 seconds. So our del t prime becomes 4 gamma. And then del t prime also is given in the question as 5 seconds. So that is given here. I can put 5 in this place, substitute this with this information. So I have 5 is equal to 4 gamma, and therefore my gamma is equal to 5 by 4, which is 1.25. So I have got the gamma factor here. So my del x prime therefore is going to be equal to minus 1.25 times u times del t is 4 seconds, so 4, right? Del t is also given for me in the question as 4 seconds. So this is again going to be equal to minus 5u del x prime. Okay, now I can calculate u based on this, right? So how do we calculate? Gamma is here, so gamma is equal to nothing but square root of 1 over square root of 1 minus u squared over c squared, which is equal to my 1.25 here. So I square both the left and right hand sides, and then take it to the other side. So I will have 1 minus u squared over c squared is equal to 1.25 squared, and that will be again taken as one more inverse, so that will be 0.8. So my u, if I simplify this, will get answer 0.6c. Please verify that one. This is 0.6c. So now I got the velocity of relative motion. Now I can substitute here this u value to get my del x prime coordinate, that is minus 5 times 0.6, that is 0.6c. That is going to be 3, right? Or 0.6, right? So 5 times is minus 5 into 0.6 into 3, right? Because c is 3 into 10 power 8, so it is minus 5 into 0.6 into 3 into 10 power 8, because here is c, right? So del x prime therefore is going to be equal to 3 into 9 into 10 power 8 meters minus the negative sign. So we were asked to find the spatial separation of the two events in the s prime coordinate. So the spatial separation in the s frame was given as 0, but in x prime they are separated by a large distance. And the time separations in the two frames are just 1 second, because in s prime it is 4 seconds, s prime it is 5 seconds. So this is the spatial separation in s prime frame of. Okay, let us continue to do the sixth problem. Two inertial frames S and S prime are in the standard configuration with a relative velocity of 0.8 c. If an event occurs on the x prime axis with coordinate x1 prime as equal to 1500 meters and t1 prime is equal to 5 microseconds, what are the coordinates x1, y1, z1, t1 of the same event in S frame? So here the coordinates are given in S prime initially, and then we have to use Lorentz transformation to get the coordinates of the same event in S prime frame. This is for one event, right? If a second event occurs at S prime with these x prime coordinates, what are its coordinates? In the S, that is reverse. So we have to use both Lorentz transformation and inverse Lorentz transformation in this particular problem. Now, what are the time intervals between the two events in these two frames of reference, S and S prime? That is the question here. So first let us start doing for the event 1. For event 1, which is the first part, right? In S prime, what are the coordinates? Because yes, the coordinates are given as 1500 is in S prime, right? So it is for event 1 in S prime, x1 prime is equal to 1500 meters, and then t1 prime as 5 microseconds, so 5 into 10 power minus 6 seconds at the right of it. Here y1 prime and z1 prime are not relevant because the motion is around the relative velocity is around the common x-axis with 0.8. See, u is 0.8, c therefore. So once we know u, it is always handy in relativity problems to calculate gamma. So if I get gamma as 1 over square root of 1 minus u squared over v square c squared, that is 0.64. C square will cancel, so my gamma I get as 0.36. 1 over the square root of 0.36 is 0.6. And if I do it, it is 1.67. Okay, now I want same event 1 in S frame. Event 1 in S frame is x1, and that is going to be equal to gamma times x1 prime plus u t1 prime. So x1 is equal to 1.67 times 1500 my x1 prime plus 0.8 c, so 0.8 into 3 into 10 power 8 my u times my t1 is 5 into 10 power minus 6. So my x1 I get as roughly it is actually 4500 meters. So exactly if you want to calculate, you can have it as 4509 meters. Approximately it is 4500 meters. Now similarly I can calculate t1, which is gamma times t1 prime plus ux prime 1 prime rather over 6 square for the first event, right? So again if I work out, I'm getting about 15 microseconds in this case. Let's check this one out. That's right. 15 microseconds. Now the question here is second event is given, right? So that is the second part. That is the A part we have solved here now. Let us move on to the B part of the problem. That is the second event coordinates in the S prime are x2 prime is equal. That is also is also given in the same thing S prime frame only. So we have to use again inverse Lorentz transformation only for this as well. 10 microseconds, right? It is given. What are x2 and t2s here, right? That is the question here. Please to check the problem again. So x2 is again gamma times x2 prime plus u t2 prime. It is the second event, right? So if I again substitute the numbers 1.67 for this, x2 prime is minus, here minus sign is given, so minus 1500 meters plus my u is 0.8, my c is 3 into 10 power 8, and the t2 prime is 10, so 10 into 10 power minus 6 because microseconds. If I work this out, I get x2 as equal to 1500 meters approximately, that is therefore 1503 actually. So the two events are separated by that will come to later. We still have t2, right? So t2 we have to calculate, that is gamma times t2 prime plus u x2 prime over c square, which is equal to 1.67 into our t2 prime is given as 10 microseconds, so I'm putting 10 into 10 power minus 6 here, plus u is 0.8 into c is 3 into 10 power 8 into x2 prime is 1500 minus 1500, so it is minus 1500 over c squared, right? So 3 into 10 power 8 whole squared. It's directly cancel, and we have to work out the remaining terms. If you work out the remaining terms, please do the calculations. I find that this again 10 microseconds. Right now, we want as a last step the difference between the two time coordinates in the S frame. That is the time coordinate for the second event minus the time coordinate for the first event. That is T2 is 10 microseconds. We calculate the T1, we calculated already as 15 microseconds. Therefore, the difference del T in this case is minus 5 microseconds. And this implies that the solution negative sign we have got. This implies that in the S frame, the second event occurs first. That is, whatever was second event for the S prime frame, it occurs first for the S frame, and whatever was the second event for the S prime, that occurs as first. It's very interesting if you really ponder over it. In special relativity, there are situations where the order of events can be altered. The order of events can be reversed. So here we have the situation where the order of events are reversed between S and S prime. Now some people may wonder, does this not affect the causality? No, it nowhere affects the causality of events, because if the two events are either time-like separated or light-like separated. To know what is time-like separated, light-like separated, and space-like separated, please do watch my lecture video on this channel. I've discussed those concepts very clearly there. Please go and check out there. So if the two events are not either time-like separated or light-like separated, then there is no causal connection between the two events. So if the two events are space-like separated, which is true in this case, then there is no causal connection. Causally, they are cut off. If the two events are causally cut off, the order in which the two events occur between two inertial frames could be reversed, and that is what we have here. And that is why here the second event occurs before the first event for the observer in S frame of reference. That I find very interesting for the observer in S frame of reference. Let's move on to the next one. A neutral K meson at rest decays into two pi mesons which travel in opposite directions along the x-axis with speeds of 0.828 c. If instead the K meson were moving in the positive x direction with a velocity of 0.486 c, what would be the velocities of the two pi mesons? This is the question. So first we have a situation where we have neutral K meson, right? One neutral K meson. It splits into two pi mesons. Pi meson A, pi meson B, let us say, right? And they each go with the velocity 0.828 c. Okay. If instead the K meson were moving in the positive x direction already, because it was originally at rest, if it were rather moving originally with the velocity u 0.84 or 0.486 c. Now what would be the velocities of these two mesons? Here we can say that we can fix a frame of reference to the K meson, and since it is moving, we can say that that's the relative velocity, and then we can calculate the velocity of these two objects in that frame of reference, right? So let me say that In this case, let S be the frame of reference, right? Fixed to the K meson. K meson. At rest, right? That is the original case. So now I can fix the moving frame of reference S prime. So I can say that S prime be the frame of reference fixed to K meson again, moving at that velocity is given as, I think, 0.486, right? So 0.486 c. Therefore, the relative velocity between these two frames S and S prime is u, which is equal to 0.486 c. Okay. So if that is the case, we can simply apply one set of equations, Lorentz velocity transformation equations, and solve this one. So I'll say it is right here. We need velocity of the objects, right? So we can say that let us say this is a velocity for the meson, pi meson A, which is obtained from the split between split of a K meson, right? So V A prime is equal to, in the S prime A prime frame I need, because I want two particles here. So the first particle I labeled as A. So I say first pi meson A is V A minus U over 1 minus V A times U over C square. This is equal to, the velocity is 0.828 of the pi meson. So 0.828, each one travels with the same velocity, 0.828 c minus U is 0.486 c over 1 minus the product of these two. So 0.828 multiplied by 0.486, c squared will cancel, so this will remain. So if I do the calculations, I get VA prime as 0.57 c. So this is the velocity of pi meson, okay, A, with respect to the frame in which it is moving along the x direction, because here K meson is moving in this direction with this velocity. That is what means, right? Since we have fixed our S prime to that. In this frame, K was at rest, and therefore this became our relative velocity. So here now, if one K meson is initially moving like this, and then it emits pi meson in opposite direction with 0.828 between them, then with respect to this K meson, the velocity we have found as 0.57 c. Similarly, for the other pi meson, VB prime is going to be equal to VB minus U over 1 minus VBU over C squared. So if you plug in the values, you will get 0.94 c. So that is the velocity of another pi meson that is going in the opposite direction with respect to this K meson. So that is 0.94 c. Okay. So next question is, a rod in the frame of reference of observer O makes an angle of 31 degrees with respect to x-axis. Another observer in a frame in relative motion along the positive x direction with the first frame measures the same angle to be 46 degrees. What is the relative velocity between the two frames? It's a very interesting problem. Because here you have a frame of reference where observer O is there, let me call he is at the origin, and let me call that frame as S frame of reference. Now, in this frame, a rod is there positioned, let us say at the origin, doesn't matter where it is, but and it is making an angle 31 degrees in this frame for observer O. Now, if an observer is traveling in another frame of reference, moving with a relative velocity u, let me call that frame as S prime, and if he measures this angle with respect to his frame of reference, he would measure that angle to be 46 degrees. Okay, so in his frame, from his frame, if he measures this one, that would be 46 degrees. That is the question here. Now we can say that there is no orientation of the frames of reference here. Please understand that. There is only relative motion in the x direction, and there is no orientation, so it is not Lorentz transformation with respect to rotation, which is also possible with our equations, but it is not the case here. It is just that in relativity, just the relative motion between the two frames alone can give rise to such measurements of same angle as two different angles by two inertial observers. That is the point here. Now, how does this come into force here? That is simply because if you think about it, the x coordinate is going to be different measured because of the length contraction, the one direction, x direction along which the motion occurs, as measured by s and as measured by s prime is going to be different. And because of that difference, the angles can vary here, right? So that is mainly because of length contraction. So I can say that in the frame of reference S, the length of the rod, let us call that as L. So I simply say rod length is equal to, we know that if this is the L, then we have two components for that, Lx squared plus Ly squared, using the Pythagoras theorem. So in S prime, the rod length is going to be L prime, and that is going to be square root of Lx prime squared plus Ly prime squared. Because for him, the different x and y is possible. But the y components in this direction are perpendicular to the direction of motion, so the y components are not going to be different. So our Ly is same as Ly prime. There is no length contraction in that particular direction, right? Okay, so in that direction there is no change in length. So what we can say is, therefore, the length contraction occurs along the x directions only. So we can write these equations again as the length for the x direction here, this length is contracted. If it is Lx prime, it is a contraction of the original length Lx by the Lorentz factor, that is 1 minus u squared over c squared, isn't it? Right? This is the length contraction expression we are using. Now the angles are given here. That is the first angle, if I raise 31 degree, tan of 31 degrees is going to be a ratio of the lengths, right? Similarly, tan of 46 for the other one, the other coordinate, the other frame of reference S prime is going to be a ratio of the two sides in this way, right? Ly over Lx here in this case, and then here it is Ly prime over Lx. Now using these two also, we can again say that since our Ly is, we can write from here as Lx tan 31 Here I can write Ly prime as Ly, Lx prime rather, tan 46. Therefore, these two are I can equate because Ly and Ly prime are equal. So I can write L x prime tan 46 is equal to my Lx tan 31. Now if I substitute this in this equation, Lx square root of 1 minus u squared over c squared is equal to Lx tan 31. Of course, tan 46 is here, sorry. Tan 46 is equal to Lx tan 31. So now I can say that these two are cancelling. So I have my square root of 1 minus u squared over c squared is equal to a ratio of the angles, so it is tan 31 over tan 46. So if you plug in these values and take a square on both sides, you can get u. We find that u is 0.81c in that case. Right, so that's how we can solve this problem. Right, the next question is, two events are occurring in inertial frame S with the following coordinates. Event 1 has the coordinate x1 as a, t1 as 2a by c, y1 is 0, z1 is 0. Event 2 has coordinates x2 as 2a, t2 as 3a by 2c, y2 as 0, and z2 as 0 again. In what frame S prime will these two events appear to occur at the same time? And the part B is, in what frame S prime will these two events occur at the same place? So two different conditions are provided here. Event 1 and event 2, two events are occurring. Now we have already seen that in another situation, the differences are taken generally as del x between two frames, two events, that is 2a minus a. So I can clearly therefore use that idea here and try to solve this one. First case A, let us say. The events are occurring, they're asking what frame K prime or S prime here in this case, in what frame S prime this is occurring at the same time. So I say that del T prime in that case has to be equal to 0. So in our original equation of del x prime, if we write, we know that according to the Lorentz transformation equation is del x minus u times del t over square root of 1 minus u square over c squared, which is gamma times del x minus u del t. Here if del t we have this del t separated here as the difference between these two, right? So del t is equal to 3a over 2c minus 2a over c, that is minus a by 2c, a over tc is del t. In S frame, this is some S frame, okay, this is in some S frame. But in S prime, this is equal to 0. So we can say that. So for the first part, since same time, it is del t prime that is equal to 0. And this gives me, from this equation, I can write del t prime equation, right? So del t prime is equal to gamma times del t minus u del x over c squared. Since del t prime is 0, this time it is 0 here, this particular term. So I can write del t as equal to u del x over c squared. Okay. Okay. So I can use that now and solve that. So from that I can write u as del t c squared over del x, which is equal to del t we have calculated as minus a over 2c, right? A over 2c, yes. And then c squared, because in the previous page if I check, del t is minus a over 2c. So I've used this equation in the next stage to get u on one side and del t c squared over del x on the other side. So it is like this. C squared is to be written here. So c squared, the whole thing over del x. What is my del x here from the given this thing? X2 minus x1, that is 2a minus a, so that is going to be a. So del x is a here. So if you work this out, the c squared and c will cancel, and this will be just c and minus this thing. So minus c by 2. So S prime is a frame which is moving at relative velocity u is equal to minus c over 2 with respect to s. In such a frame, the two events will occur at same time. That is, del t will be equal to 0. That is the first part of the question, right? So if you go back and check the first part of the question, in what frame S prime will these two events appear to occur at the same time? And that is a frame S prime moving at velocity, relative velocity u is equal to minus c by 2 with respect to S prime. Okay, so in such a frame, the two events will occur at the same time. Those two events that are separated by this time interval in S, right? Next part of the question, in what frame will the two events occur at the same position? That means in this S prime this time, or let me even call that as S double prime now, no problem. In this particular frame of reference, del x double prime is equal to 0 because it is given as same position. So I say that in what frame, let us call the double S prime then, right? For convenience, will these two events occur at the same place? That is some del S double prime frame in which del x double prime is equal to 0. That means in our equation, del x double prime is equal to gamma times del x prime minus u del t prime, right? Of course, in this case, the confusion is with the original thing, so we can retain this. In that case, del x is given as a separation, right? So that is a here. So if this turns out to be 0, then we have an equation del x prime is equal to u del t prime. So u is del x prime over del t prime, and that del x and del t prime have to be taken from the question only because that is our x prime frame in this case, isn't it? So that is the difference we have to take from here. So if you take that, that is u is equal to, we know that the first difference is this is a, right? Difference in the coordinates is a over del t prime is the difference in times, that is minus a over 2c. So if these two things cancel, we get minus 2c as the u. So this implies that a frame of reference that travels at twice the speed of light in the opposite direction, in such a frame of reference, the two events will occur at the same position, and no such frame of reference can exist. No such frame can exist. So the comment that I can make on this is no such frame of reference S double prime or S prime, whatever you want to call that, exists. No such frame exists where its relative velocity with respect to another inertial frame can be minus 2c. No, that is not possible because relativity forbids any frame of reference from traveling at twice the speed of light. Nothing can cross the speed of light. For any inertial observer, no measurement he can make can be faster than the speed of light in vacuum, that is c. So we can conclude that in this case, such frame of reference cannot exist where the two events occur at the same position. That's the conclusion we can draw from that. Right, let's move on to the 10th problem. A light signal is sent from origin of a system S at t is equal to 0 to the point x is equal to 3, 5 and 10 meters respectively x, y, z. At what time t is the signal received? At what time t prime is the signal received for an observer in another frame S prime moving with the relative velocity 0.8 c. From these results, verify that the light traveled with a speed c in S prime frame also. So the question here is, we have a light signal. So let me try to draw a frame of reference. This is S, and in this frame of reference, of course, there are three coordinates x, y, z. A light signal is sent from the center origin at t is equal to 0. Here, let us say it is starting. This light signal expands, let us say, a spherical wave and reaches a point here, which is at 3 meters along the x direction, 5 meters along the y direction, and 10 meters along the z direction. So the coordinates in my case here are 3, 5, 10 for the x1, xy, and z coordinates. Now t is asked what time this will, because we know that light takes a definite time to travel from one point to another point. Here the origin is at 0, 0, 0, right? So from this point to this point, definite time light will take to travel, and that time is t. And that time is going to be equal to the distance that light has traveled in the time over the speed or velocity with which it travels. Right. So the distance in this case, let us call that as d, and that is going to be equal to x squared plus y squared plus z squared. Okay, so it's special relativity, so we don't consider any space-time curvature here. So a regular mathematics, so to say, is applicable. So here we say that t is equal to square root of 3 squared is 9, 5 squared is 25, and 10 squared is 100. So square root of 129 is our distance light travels with the speed c. So we can say that our time for light travel is equal to root 129 over speed is c. So that is root 129 over 3 into 10 power 8 meters per second. We do that, we get answer in seconds. So if we do this calculation, we get 3.79 into 10 power minus 8 seconds light takes to travel from 0, 0, 0 to 3, 5, 10. In S frame. Now there is another part in this question, right? And there are two other parts actually. So let's deal with the B part first. In B part, what is asked? In another frame S prime, the coordinates of this event is x prime, y prime, z prime. And if that frame moves at a speed of 0.8 c, what are these coordinates? That's the question. So for that, first we have to calculate the relativistic factor or the Lorentz factor gamma, which is 1 over square root of 1 minus 0.84 squared, 0.8 squared rather, sorry, 0.8 squared, c squared over c squared. So it is going to be 1 over square root of 0.36, that is 1.67, we know it. Now x prime is equal to gamma times x minus u t, which is equal to 1.67 times our x is 3 meters, so 3 minus u is 0.8, so 0.8 into 3 into 10 power 8 times our time we have calculated t as 3.79 into 10 power minus 8. So if you do the calculation, we get the x prime coordinate in this particular case to be equal to a nice round minus 10 meters. Please check this one out. Okay, and then we can calculate the y prime and z prime. Oh, we don't have to calculate because they're not changing. So y prime is the same as what is given in the question originally for the y coordinate. Is I think 5 meters. And z prime is also not changing, that is same as z coordinate in the S frame, that is 10 meters. So these are not changing. Okay, so what do we have here? So we have got the coordinates for the same point in S prime frame of reference. Now what is the speed in that frame? That is the third part. So the part C of the question is verify that speed of light in S prime frame is c. So again here if you want speed, it's distance by velocity by time, right? Distance by time. For that we have to calculate time. So what is time here? T prime is equal to, we haven't calculated that, that is gamma times t minus u x over c squared, and that is 1.67 is gamma times our t is 3.79 into 10 power minus 8 minus 0.8 into 3 into 10 power 8 into our x given in the question as 3 over 3 into 10 power 8 whole squared. So this 3 and this one thing square will cancel. The remaining things is 2.4, 3.79. So it is 1.67 times 3.79 minus 2.4 because 0.8 into 3. Okay, we have another thing here also, so that also goes to the denominator. So we can cancel this 3 and this 3. So it is basically 0.8 into 10 power this my 8 here in the denominator goes to the numerator becomes minus 8. So into 10 power minus 8. So if we do the calculations, we get 5 into 10 power minus 8 seconds. That is the time prime. So now we can say that in this equation, I want speed of light or speed generally as distance d, that is d prime here, right? D prime over t prime, let us say. My d prime is what? Square root of my coordinates x prime squared plus y prime squared plus z prime squared over my t prime. Okay, so for lack of space here, I'm going to try to squeeze this here. If I do the calculations here for t speed is equal to square root of my x prime, I have calculated to be 10, right? So it is 10 squared, that is 100, plus y prime is same as what is given in the question, that is 25, because 5 squared, and then this is again another 10, so if I square it, I get 100. My t prime I have calculated to be 5 into 10 power minus 8. Here this is square root of 225 over 5 into 10 power minus 8. So my speed is equal to 15. Square root of 225 is 15 by 5 into 10 power minus 8. So my answer is 3 into 10 power 8 meters per second is the speed of light. So we have verified thereby that the speed of light in S prime frame is also 3 into 10 power 8 meters per second. So that confirms the Einstein's second postulate in special theory of relativity, that the speed of light for any inertial observer in any frame of reference has to be the same, is c. So that concludes the problems on Lorentz transformation. Thanks for watching.